Okay, so the other issue, of course, is to provide explanations. So you decide to make a plan that is optimal with respect to your model. That is, the robot decides to make a plan that's optimal with respect to your model, with its own model, and then tries to see how to make the human realize that this plan is optimal for them too. And to do that, it needs to say, these are following changes. Change this precondition from the action. Add this precondition to this action. Remove this effect from this other action. So those are the deltas. You need to compute these deltas. Okay? And that deltas are the explanations. Okay? And this plan still has to be optimal with respect to the robot's model. And once the deltas are applied to what it thinks is the human's model, then it will also be optimal with respect to the human's model. Okay? Computing the epsilon is an explanation process. Now notice that there is a degenerate solution for this. If ever anybody asks you, why the heck are you doing what you're doing? Say, take my head, put it into your head, then you'll understand what I mean. Which is basically the robot saying, here's my entire model, take it and change your model, throw your model out, take my entire model, and use that to see whether or not I'm out. That is actually, the problem with that is that would be an explanation that's way too long, and it's basically, those are not things that we consider explanations. We want, psychologists have talked about good properties for explanations, one of which is conciseness. You want to provide only the pieces that are relevant to make the other person realize that the behavior you have shown is actually optimal with those changes. Okay? So that is something that you want to keep in mind. So in this particular case, in the same example, essentially, if the audio was on, you would see that it's yelling at the top of its head voice saying a certain path is impassable right now. So that's the only thing that you have to change in your model. A particular connection is now missing. And if you remove that, it turns out that the next shortest path is the one it's taken. And so the explanation will be understood. Now, there is one other piece. I said earlier there are like two pieces to think about. One is degeneracy of the explanation. The other is something that we take it for granted, but which is inferential complexity. It's not obvious. Even if I have the model, the correct model, it's not obvious to see that what you're doing is optimal with respect to the model I have. That's, of course, unless you have, all of us have FF, some of these planners running in the background. And of course, as you know, when they do run in the background, they take forever to actually complete because of the complexity of it. Okay, so inferential complexity is something that we want to take into account. But for now, assume that we actually, in this part, we're assuming that that's basically, once I give the changes, and the human will be happy as long as the plan is optimal. In this particular map scenario, it actually is true because it's a simple enough map that the moment you tell them this particular path is closed, they may say, yeah, that's our next option. Okay, so although I've been showing like moving robots, you can do this also in the context of actually supporting, planners supporting, decision making for humans in the way. This is the stuff that we did, that we do for the NASA project. I won't go into details other than to show that there's a paper actually a couple of years back, and also I think last year in Spark and UISP on how to do the same kind of a theory, but to provide suggestions how to generate plans, how to help the human generating plans, as against doing collaborative behavior. So in this case, this is not an embodied robot; it's just a planner working as an assistant to the human. Okay. This is something that I'm sure people before coming into this room must have heard a lot about XAI. Explanations are like the big thing suddenly, all of a sudden, right? There's this DARPA project that's partly responsible for it, and everybody is always worried that, oh my God, AI is inexplicable, and what we know what's going to happen. XAI is hard, but mostly really as a debugging tool for inscrutable models. Okay? What happens basically is if you say there is a dog playing guitar in this picture, if your machine says that, and oftentimes they're used in the vision examples. So then you say that, and then you ask the machine, how come there is a dog? How come there's a guitar? And so it shows here is a point. I point the guitar here, I'll point the dog's face here, and so on. So this is called pointing explanations. it's like the least evolved type of explanations. If we had to explain what we did by pointing to things, we would not be where we are. Okay? In fact, pointing explanations are primitive. Explaining decisions this way, like for example, Rao, why did you think you would take the morning flight to come here as against yesterday evening's flight? That's a decision I made. How do I explain this to you? There's a simple picture. There's a space-time tube of my life. And then I would say, look at this, look at this, look at this, now you understand. It's a very primitive way of explaining things. We are impressed here because we have not had any AI systems doing well in vision tasks for such a long time that it's like a novelty item. In particular, it's kind of, this is by the way from a paper called Line, where they, for example, show that in this particular case, the system says this is an Alaskan Husky, and you ask the system, why do you think it's an Alaskan Husky? And it shows the snow. And you say, see, I found there's a bug in the program, because you're thinking if there is snow, then it's an Alaskan Husky. Okay, this is the kind of flag-bearing examples of explainable AI of the pointing type. First of all, I want you to understand that's kind of a silly thing, right? Because actually there is this whole entire idea called adversarial examples. I don't know how many of you have seen this picture. Pretty much everybody in AI has seen it, but I'm not sure in this room whether everybody here has seen it specifically. But so here's a school bus. You add some imperceptible noise to it, and I get this, which, as all of you know, is an ostrich. This is what state-of-the-art, basically ImageNet winning recognition systems will say that it's an ostrich. By the way, this is not something I made up. This is obviously known. This is adversarial examples is a huge problem in computer vision in general, because you are essentially have a huge overfitting problem in general. Okay, and you are happy as long as the machine agrees with your decisions, but you have no clue why it is thinking it's a school bus to begin with, and so obviously you have no clue as to why it is thinking it is an ostrich. So we should ask it to point out, can you please point out the ostrich parts in the school bus? If ever you think explanations are pointing, think about that kind of an example. One is of course the space-time tube, the other is, this case essentially our vocabularies are completely different. We have no actual idea as to what the system is doing. It's an inscrutable system, and you're just hoping that pointing is possible. And clearly, there is nothing you can point, on this school bus that will convince anybody that it's an ostrich, unless I'm missing something. Okay, so keep that in mind. And so while this is useful in some cases, and at least you can argue that if there are no adversarial examples, then maybe at least this works. This is of course the flagship poster child of XAI in vision, right? But first of all, ask yourself the following thing. How often did you ask your friend, why did you see a light here in this picture? You showed a picture to your friend and asking, can you explain why you see a dog here? Can you explain why you see a light here? You're always asking your friends, why did you take this flight? Why did you not get done with MS instead of joining PhD? These are the questions you ask. You never ask visual explanations generally. Okay, it's worthwhile keeping that in mind. And explanations are critical actually for collaboration, which are sequential decision-making problems. And this is the community that is actually has something to say about it. But they are not, and then it's neither a solidarity by the agent. In fact, one kind of explanations that has been done a lot in our community is you make a mistake and ask the system, please explain, and out comes 50 pages of output. And then you just go through it line by line by line and say, well, those are explanations that for people who have no other life. Basically, they are debugging computers. That's why debugging explanations are useful. If you're writing a program and it's not working well, you need to debug it. If you have a friend who has to debug, get a new friend. Right? So when we are collaborating with people, we don't do debugging explanations. Okay, so keep that in mind. So explanations are critical for collaborations. They are not a solidarity. It's not you talking to yourself saying, look, this is a trace of my reasoning. It makes sense. Does it make sense to you? And it's like explanation by exhaustion. People give up and say, oh my God. And they also are not explanations by pointing. And in fact, the kinds of things we are doing is one step which I obviously think is reasonable. model reconciliation view, it comes closer to the psychological theories of explanations. For example, psychologists have talked about contrastive properties of explanations and conciseness of the explanations, and the fact that explanations are tailored to what you think the other person believes. Doctors, when they come to a decision, explain it in one way to the patients and a different way to their own other doctors, because they have different vocabularies and different models. So explanations are always with respect to the models. And it's worthwhile to keep that in mind. So in our own scenario of model reconciliation, it turns out that we can come up with a variety of different kinds of explanations, which are all changes to the model, deltas to the model, such that the new plan would be optimal, but they have different other properties. In particular, model patch explanation is this degenerate explanation I mentioned to you, which is just give your entire model to the human and say, start using this. That will have too many irrelevant changes that you are providing. There's nothing wrong with it, but it's just cognitively too much of a burden. So they'll never again. This is actually, we're all teachers, right? Some of us are teachers. Anytime students ask you to explain, you try this. You basically just sort of give a long-winded, 1 hour long explanation. They'll never again ask for explanations. And the semester goes much faster that way. But clearly, that's like a silly thing to do. Plan patch explanation is just basically looks at the actions in the plan and only tries to look at connections with respect to that. In some sense, one of the first things that we'll be looking at is this idea called minimally complete explanations, which are these changes to the model. If they are done to the human's model, then the human will see that the plan you have made is actually optimal with respect to it. Okay? But it turns out that the minimally complete explanations don't have this other property of monotonicity, which is after you explain this example, you continue to work with this other same person, and something else happens, they ask for another explanation. Now, based on this explanation, they realize, unless they have no memory, that the previous explanation is bogus. Okay? To give you an example of that, let me say in this case that we looked at before, which is this fetch word. Suppose the first time, then basically the human asks, why the heck are you doing this song and dance about lowering yourself and tucking your hand underneath? And one explanation could be the minimum change could be just, well, remember that move action has a hand tuck as a precondition. Remember that it's not there in the human's model, right? If you just tell that, the human will keep quiet. Yeah, now that makes sense because hand tuck is required and hand tuck requires tucking action and you're doing that, it makes sense. Okay, but later on, imagine that they also realize that you need to crouch. In some other case, you wind up saying that, to do something, you have to actually crouch down. At that point, they'll say, well, turns out that previously you said only hand tuck, and now you're also doing crouching, so you must have done this extra action of crouching. How come you didn't do that? Because the crouch gives crouch as the effect for the human. Okay? You wouldn't have done that if you had told upfront itself that actually both hand tuck and crouch are preconditions, which is a little bigger explanation, but it's monotonic in the sense it doesn't change because of the next problem. This is assuming the robot's model is still not changing. The human's model and the robot's model are same. It's just that as the new problems come, the previous explanations should go out the window. You see what I'm saying? That's the monotonicity. Again, if those of you who are thinking in the background, we do this. Oftentimes we give explanations that are expedient, just to stop people from asking us questions. And then that sometimes can lead to loss of trust, because a later problem explanation makes the previous explanation invalid, and then they'll say, well, you must have made up the previous explanation. Okay? So that's something that you want to keep in mind. Now, all of this is done at a level where I was thinking somehow you can compute these deltas. We are in high caps, nothing comes free. This is a search. It turns out it's a search in the space of models. It's not a search in the space of a single model. It's not a search in the space of action sequences given a single model. It is a search in the space of models itself. There is our happy robot with its MR, there is your human with the MRH, which is their expectation of the robot's model. And the idea is you are trying to find a model in between where the edges, of course, are changes, specific, add, say, do this, add this precondition to your model, remove this precondition to your model, add this effect to your model, remove this effect from your model. Those are the edges, okay? And you're doing search over this space, and it turns out that that minimally complete explanation and the minimally monotonic explanation wind up differing in terms of the way you search on this space. So in one case, essentially in the MCE, you can start with the humans model and look for the first model after some number of changes, okay, which actually makes the plan that the robot has optimal. When I say you, it's the robot doing all this search. And then once it finds it, then it just needs to provide the distance between this and this other one, which in terms of the deltas. That's MCE. To get the minimally monotonic explanation, you actually start from the opposite direction. Start from the robot side, keep making changes until the point the plan is no longer optimal. And so the last point where the plan is no longer optimal, last point where the plan is still optimal on this path is here. So these are the changes that you can do. You see what I'm saying? If you do that, then you don't have to change your mind with respect to a later problem. Okay, so it would be monotonic. So all this stuff is in an Ichkai 2018 paper, and it turns out it's a crazy search. Everything is bad for us, and we start with Loxworld, which is p-space complete, and so we are stuck anyway. This is model space search, so it's obviously complex. So finding explanations is not necessarily going to be easy. So you may have to come up with approximate explanations. Here we're just talking about the complexity of the problem itself, and it turns out there is some structure in this search that you can exploit, and so that can be used to improve the search a little bit more, and that's out there in the Ichkai paper. Okay, so that's 2 points. The next thing, of course, is a very short part, which is explicability and explanation are not 2 completely different things. Actually, it turns out that as Southwest once dropped way too far away from my gate, and they kept taxiing to get to the gate, and they said, we are cheap because we fly you half the way and taxi the rest of the way. So similarly, explanations and explicability can be combined by changing the human's model up to a particular point, and then say, be consistent with respect to that. You see what I'm saying? And you could do this in cases where the humans are much less willing to take certain kinds of differences in the model. So you keep those differences alive, and then you become conform to them, but then at least you are not being conformed with respect to this model. And so it's an interesting new search. It's a trade-off between the 2 explanation options. So there is a paper, actually in fact this work was done a year or so back, and there's an extended abstract in AMAS, but there's a full paper, Ichkai, you can hear the whole paper, but it's also available on the web. Okay, so that's basically trading off explicability and explanation. There is a different way of trading off explicability and explanation. Here we still try to look at this search space and try to think of which model do I come to, and then become conformant. A different idea is you realize that you can have epistemic actions whose only effects are changes to the knowledge state. You can actually realize that explanations are really just epistemic actions. All you did when you gave this epsilon is the world didn't change, the human's model changed. Once the human's model changed, the human was happy because they were able to see that the plan that you did was actually optimal. Now, of course, only in ICAPS can you say, let's reduce it to epistemic planning. It's like saying, let's reduce it to halting problem, and then we'll be really happy. Of course, because people have avoided touching epistemic planning because it's even harder than the problems that we look at. However, Sharad, who is a brave guy, actually has, working with Christian Musi and others, basically has found that for the problem that we currently have, there is not infinite nesting. Basically, there is like a one-level nesting, and in fact, epistemic planning in this area is not as bad as it could be. And so, if you use this approach, and in fact, I believe if I'm not mistaken, this might be presented in XAIP tomorrow too. But if you have that case where you are providing explanatory actions along with the causative actions. So you're doing actions that change the world while talking about what you're doing. And those are self-explanatory plans. And you could do that too. And if you do that, you're essentially combining explicability and explanatory into one single framework. That's kind of cute. In doing this, actually I'm running out of time, so I'll kind of go faster on this, but there are some nice videos, so we just have to probably skip over those. But in doing this, one of the things is, we also looked at the idea of doing intention projection during the planning, which is during the plan execution, you can say, this is what I'm trying to do. And that's essentially self-explaining plan, okay? And there's actually, since we're talking about intention projection, this is also intention recognition, and so we played, you can do intention recognition projection just based on natural modalities, such as listening to what people say in natural language, for example, but you can also do it by just looking at their faces, and you can also get lazy and do what we're doing here, which is sort of a primitive brain-computer interface. It's not at the level of neural link. This is basically just trying to show sense enough to, for example, realize here that this guy has decided he doesn't want a certain block to be touched by the robot. And without saying it, you can sense that, because in fact, it's not surprising that it's doable. And once you do this, so this is actually the guy sitting here, you can ask him how he felt when he did this, but he's very happy when both because it caught his message and we didn't kill him when doing the problem. But so this is something that we can do in terms of intention recognition using these kinds of augmented reality, brain-computer interface of things. And here we try to do for the intention projection, instead of just doing natural language assertions, you could do augmented reality, you could do HoloLens. Okay, I mean, many of you are probably familiar with the HoloLens, where you're seeing the world as well as doing additional things that the program is projecting into your visual cube. And we use this in an IRAS 2018 paper, for example, to show that in this particular case, the robot, let's say, is trying to make a particular word. And it's one of these words. These are the words that can be made with those blocks. But it really is trying to make the word brat. Okay, and how does it make sure that you get the idea that it's trying to make the word brat? So one thing that it's doing in this particular case is it's putting a little marker, a green marker on the block R. The block R is actually embodied, it's a real block in the real world. The green marker on the other hand is an augmented reality marker. Okay, showing that it can be done is more of Microsoft contribution because they have the HoloLens and we could buy it. Figuring out what to show is the planning problem. Okay, and so if you want to figure out how those things are done, essentially look at the IRAS 2018 paper. There is more of this here. I will also skip over this interactive plan execution. There are a bunch of other things to cover. One thing that I want to mention in the context of this is, how does the AI agent get the human model? I focused, being a planning guy, I focused a lot more on the inference part. I did mention that in some cases, you start with the same ground model, and then the robot can at least track how many changes happen after, which is what happened in the original in the search and rescue scenario. But in other cases, if the robot doesn't know the model, it can learn the model from traces. We have work, of course, in learning PDL models from traces. You don't necessarily have to learn PDL models. We have also shown that sometimes it's actually cheaper to learn shallow models, which are not which don't have causal analogy there. And they wind up being effective enough in certain cases. So it's like a strange situation where machine learning people will only get correlational models and they're trying to run away from them to go to the causal models. We only want causal models because we pay people to come up with these models and give it to us. But we don't necessarily need them in some cases. And it's actually a useful middle ground to look at. And then finally, often there may be shortcuts. You don't actually have to learn the model at all. You can learn things like the labeling function that I mentioned, for example, for the explicability. I didn't learn the model, I just learned the labeling function. And that's actually, there is a, you can think of those are model-free explicability, which was the labeling function I mentioned last time, earlier on in the talk. But you can also have model-free explanation, which is, Sharath is going to be presenting it at ICHCAI 2019, but also will be presenting it tomorrow at XAI. Okay, so this is the part that I was making, that we, the planning people, essentially sort of tended to assume models are complete and they're causal, and we focus on inference. People from learning, correlational learning, basically just take anything that they can learn from the data and see whether or not it's sort of predictive. But there are ways in between, there are places in between where we can actually connect these works. For example, some work we did in and published in August 2016 shows that even ideas like word vector embeddings can be applied to action embeddings. So basically, you can think of a plan as a sentence in actions. And you can compute the embeddings on that. It's a very simple idea. And it turns out, actually, if you do that and use that to predict the next action, which is like a plan completion exercise, and compare it to our community's approaches, for example, Ramirez-Gaffner approach of doing plan recognition based on the model, which requires the model. That means you can either learn the model, PDL model, or learn the embeddings. And then check how the completeness performance works. And it turns out the performance is actually better for the shallow model. At some level, it's not surprising because actually you need lot one parameters to be learned from the amount of data you have when you're trying to learn the PDL model. Whereas the embeddings essentially can do whatever the best they can do with the traces that you have. So it's a kind of thing that you might want to keep in mind as, we don't necessarily have to learn fully causal models, which is actually first of all no problem to begin with. In terms of model-free model reconciliation, as I mentioned, you could essentially provide not just the traces to label for the training, during the training, but traces with an explanation action. And then see how the labeling works. And you can use that essentially to figure out what the explanatory actions actually mean to the human brain. And this is the very nice idea that Sharath did for his ICHCAI paper that he'll be talking about tomorrow. So it's really the same case, same labeling problem, but actually now you are labeling with the explanatory action thrown in. Okay. Again, that basically assumes that there are certain number of explanatory messages that are available. So in this particular scenario, this is called modern world, it talks about explanatory messages, but without knowing the semantics. And then you will see what the humans think of your particular explanations based on that case. Okay. This will be presented again tomorrow. I want to mention a little about the human subject evaluations. Of course, as I said, we should basically take actual evaluations more seriously. You should have IRBs. And what we did in our particular case, one of the things in HRI 2019, which is Human Robot Interaction Conference, which is a very nice conference for this kind of work. Basically, we set up the same sort of a scenario as this urban search and rescue scenario, except with two humans. The two humans play the human as well as the robot roles. And then you try to see how they interact in terms of what kinds of explanations they are giving to each other. So what we have basically shown is that, for example, that the kinds of explanations that the humans are giving in this scenario can actually be reasonably well classified into the MCE, MME, plan patch, model patch style explanations that we have put in as our set of explanations. So that's one nice thing. The other thing is that, as obvious as it is that if you do explicable behavior, people won't ask you for explanations. Is that true or not? It actually winds up being true when humans are working with each other. Okay? So that's the kinds of things that were shown in HRI paper. There's one other thing that actually was a small abstract in HRI this year, which says that sometimes there are multiple explanations for the same thing. In fact, you may be able to explain the same thing, which can be an MCE, which involves just one precondition change or one effect change. Which explanation do you prefer? And so they did a study, and in fact it turns out that people tended to prefer essentially explanations which involve effects more than those that involve preconditions. That's kind of it. So the last part, which I basically will flash at you mostly, is there are a whole bunch of recent extensions that we have done to the basic model. You can support model reconciliation in non-PDDL settings such as MDP settings. There's an ICHKAI 2019 paper on that. You can relate the notions of explicability, for example, that we talked about, to other notions that people in robotics have looked at, for example, legibility. One interesting thing there is that there are certain assumptions that robotics people make that because they mostly focus on motion planning, and there are different kind of assumptions we make because we focus on task planning. I'll mention this a bit, but there is a nice paper on the landscape of these definitions that will be presented on the second day of the main conference. Until now I kind of told you that if I just see the human slightly perplexed, I just give them an explanation. That's one way of giving explanations to your boss. If you do something and your boss looks kind of quizzically at you, you start talking and say, this is the reason I'm doing this. The other is let the boss ask you, why aren't you doing this other plan? Why are you doing this plan instead of this other plan? Which is providing a foil. In fact, if you wait for that, oftentimes people don't even know what else can be done, and so they won't even ask you for explanations. Actually, that's a good thing in life. But if they give you a foil, you can then actually just defeat that foil and say, the reason the foil you gave is not as good is because it's actually not compared to what I'm doing, or it's not feasible. And so there's a work on that Sharat showed in ICHKAI 2018. There actually this whole direction is that we look at it as if these are flat models. You can actually look at it in the context of hierarchical models. And the way the file is articulated can give you interesting localization about where in this hierarchy of models the humans model actually. Okay? And finally, we can also handle multiple human agents with multiple models, different models. And when you have that, this is, for people, old-time planning folks here, we can talk about conformant and conditional explanations. Okay? And there's a nice paper in 2018 ICAPS by Sharat about how to do that. And then the last thing, trust. Explanations are the way you can make people believe in a world that never was. Politicians do this all the time, and you do this all the time. So in the search that I showed you, the robot is starting from its model and going towards the human's model. Nothing stops the robot from making the human go to a different model and believe that is the reality, and in that reality what it's doing is optimal. That's a lie. And we talked about, there's a paper in AIES, AI Ethics and Society Conference, where we talked about whether people like being told lies by AI systems, if they are white lies. By the way, people who are near and dear to you are always telling you white lies just so that you will do good things, right? You want your AI personal assistant to make up stuff just so that you will have a healthier life. So we did actually an interesting human user study, and then we presented that to AIES. And then based on that, tomorrow, Tathagata is actually, that part was when can AI bots lie? And tomorrow, Tathagata will tell you what I was telling you, which is how can AI bots lie? Just by modifying the model reconciliation search. That's another XAIP paper that might be interesting. Okay, so model reconciliation for MDP's part winds up being essentially the main difference that you want to keep in mind is that in MDPs, there is actually a difference between policy